A practical problem in calorimetry. Consider a calorimeter apparatus designed to measure heat, consisting essentially of a 750 grams copper can. This can contains 200 grams of water and is in equilibrium at a temperature of 20 degrees Celsius. An experimenter now places 30 grams of ice at 0 degrees Celsius in the calorimeter and encloses the latter with a heat insulating shield. It is known that the specific heat of water is 4.18 joules per gram per degrees and that the specific heat of copper is 0.418 joules per gram per degrees. It's also known that the heat of melting of ice, the heat required to convert 1 gram of ice to water at 0 degrees Celsius, is 333 joules per gram. What will be the temperature of the water after all the ice has melted and equilibrium has been reached? So in this process, we're going to have an equilibrium temperature. So we're assuming that the equilibrium temperature will be between 0 degrees Celsius and 20 degrees Celsius so that all the ice will melt. In that case, the amount of heat absorbed by the copper can and the water in it will be Q1, let's call this mass of copper, specific heat of copper, the equilibrium temperature minus the initial temperature of the system minus T0, let's call it. And then the water inside will be absorbing heat, mass of water, specific heat of water, which will give me the heat capacity, the equilibrium temperature of water minus T0. So this will be the heat absorbed by the water. And on the other hand, I have system 2, Q2. The heat absorbed by ice will be mass of ice times latent heat of fusion of ice, or latent heat of melting, plus now it's turned into water, so mass of ice which has turned into water, specific heat of water, the equilibrium temperature minus the melting point temperature. So these two will be the heat absorbed by the two systems, and the total heat absorbed, Q1 plus Q2, will be 0. Heat absorbed by system 1 will be equal to the heat released by system 2, or vice versa. Heat absorbed by system 2 is heat released by system 1. So if we write this total to be equal to 0, so let's substitute the numbers here. I have 750 grams of copper. The specific heat of copper is 0.418 joules per degrees per gram. And then I have the delta T. So the equilibrium temperature, I don't know what it is. The initial temperature I know is 20 degrees Celsius. So not to make a mistake, let's do everything in Kelvin. So T0 is 273 plus 20, 293 Kelvin. And the melting point is 0 degrees Celsius, which is 273 Kelvin. So the equilibrium temperature minus 293, this is heat absorbed by the copper can, plus 200 grams of water inside, multiplied by specific heat of water 4.18, multiplied by equilibrium temperature minus 293, plus the heat absorbed by ice for the phase transition, 30 grams of ice is melting with a latent heat of fusion 333, and then 30 grams of ice that has turned into water is heating up to reach an equilibrium temperature starting from the temperature 273 Kelvin. So this should add up to 0. So 750 times 0.418, that is 313.5 T equilibrium minus 293, and then 200 times 4.18, 836 T equilibrium minus 293, plus 9,990 plus 125.4 T equilibrium minus 273. This must be equal to 0. So you can see that these two terms have the same factor here, T equilibrium minus 293. So if I continue this calculation, I have to add 836 with 313.5. So I will find that 1149.5 T equilibrium minus 293 plus 9,990 plus the other term here was 125.4 T equilibrium minus 273 Kelvin, which was the initial temperature of ice. So looking at the temperature terms here, so I have this one and this one, so I have to add them up. So I will get 1274.9 T equilibrium. Then I look at the products here and add up with 990. So the two products, when I add them up together, will give me 336,803.5 plus 9,990. So that was the first term. The second term, the second negative term, is 34,234.2. This has to be equal to 0. And if you solve for T equilibrium from this equation, you will see that using your calculator, T equilibrium is 283.2 Kelvin or 10.2 degrees Celsius. Now let's move on to part B. Compute the total entropy change resulting from the process. So let's look at the total entropy change. Now, in the process of the melting of ice, I have the entropy of melting, mass of ice, latent heat of ice divided by the melting point temperature. This is the heat absorbed by ice at the melting point. And then I have, when the temperature is changing, mass of ice, specific heat of water, natural logarithm, equilibrium temperature divided by the melting point. So this will be the entropy change in the ice. Then I have the entropy change in water, mass of water, specific heat of water, natural logarithm, equilibrium temperature divided by T0. And then for the copper, mass of copper, specific heat of copper, natural logarithm, equilibrium temperature divided by T0. So I will find the first term is 30 grams times 333 divided by 273 Kelvin. The second term is 30 grams of ice, 4.18, natural logarithm 283.2 divided by 273 Kelvin. Then I have for the two terms that include the natural logarithm of T equilibrium over T0, 750 times 0.418 specific heat of copper, 200 times 4.18 specific heat of water, natural logarithm 283.2 divided by 293 Kelvin, which was the initial temperature of the copper can with the water in it. So if you calculate this using your calculator, you will find that the result for this one is 2.1 joules per Kelvin. That will be the entropy change of the entire system. After all the ice has melted and equilibrium has been reached, how many joules of work must be done on the system by means of a stirring rod to restore all the water to 20 degrees Celsius? So I want to do some work on the system so that the final equilibrium will be reached at 20 degrees Celsius. Now I have 750 grams of copper, 200 grams of water in it, and then I have 30 grams of additional water in it, and my temperature is 10.2 degrees Celsius, which is 283.2 Kelvin. But I want to reach 293 Kelvin or 20 degrees Celsius. So the amount of energy I have to provide in the form of work will be equal to 750 grams times specific heat of copper 0.418 plus 230 grams of water, specific heat of water 4.18, multiplied with delta T, 293 is where I want to reach, starting from 283.2. So if you calculate this, the numerical value is 1.27 10 to 4 joules. So this is the amount of work I have to do in order to provide this energy that will increase the temperature to 20 degrees Celsius. So we have mixed a copper can, 750 grams copper can, filled with 200 grams of water at an initial temperature of 20 degrees Celsius with ice at 0 degrees Celsius, that is 30 grams. And we basically have to write the heat absorbed by ice is equal to the heat released by the copper can and water. So that's what we did in part A. That gave us an equilibrium temperature 10.2 degrees Celsius. To calculate the entropy change, there is one process that happens at constant temperature, that's at the melting point. So heat absorbed by ice divided by the constant temperature, melting point temperature, 273 Kelvin, that gives me entropy change of ice in the melting process. And once it melts, it's in the water state, m ice times specific heat of water. Now the temperature is changing, so remember the entropy change is integral. So this came from, so just a reminder, integral c dt over t between initial and final states. So that's what the entropy change is. So that gives me natural logarithm T equilibrium divided by T melting point. And for the water and copper, similarly, I have the heat capacities multiplied by natural logarithm T equilibrium over T0, where T0 is 20 degrees Celsius, T melt is 0 degrees Celsius. So that's how I calculate the entropy change. So its numerical value is 2.1 joules per Kelvin. And since the whole system is now at 10.2 degrees Celsius, I want to know how much work one has to do in order to increase the temperature back to 20. Then I need the heating 750 times 0.418 plus 230 grams, that's the total amount of water I have, times 4.18 multiplied with delta T, that gives me the amount of heat I have to provide. So this heat will come from a work done on the system. So this is the amount of energy I have to provide to the system. So that will be 1.27 10 to 4 joules.